Today we're going to look at how mountains are made on the continents. We're going to look at the highest mountains in the world, the Himalayas. How they form is a puzzle which we're going to try and solve by looking for clues. And as often happens on the Earth, when you look to the clues for one puzzle, you unearth other mysteries. And we'll end up by talking about how the continents work in general, and even where the continents came from. After all, the continents are where we live, they're what we walk around on, and we've heard very little about them so far in these lectures. I want to start by telling you a story. In the early 1800s, the British were very active in India. The frontier to their interests in India was a big range of mountains called the Himalayas, stretching all the way across the northern part of India here. At that time, the British had very little idea of what was north of the Himalayas, what was beyond them. They knew if you went far enough north, you would find the Chinese Empire up here and the Russian Empire up here. And they regarded those empires as a threat to what was to become British India. But they thought that these mountains, the Himalayas, were a pretty secure barrier preventing anyone coming into India from the north. But were they right? These mountains are very impressive. They're very high, they're very inaccessible, very difficult to cross, but things do cross them. What cross the Himalayas are rivers. There are very big, broad, fast-flowing rivers like this, also smaller rivers flowing through the Himalayas in gorges. And these rivers offer a way through the mountains. It's not an easy way. Even today, some of the ways across are on these extraordinary long rope bridges above these fast-flowing deep rivers. Not all the bridges are in very good shape. Here's one which is in a bit of a mess. Hard to cross even today, but possible. And they were worried that these rivers were a possible route for people entering India from the north. They were interested in these rivers for other reasons. The British were busy building canals and dams on these rivers, and yet they had no idea where the rivers came from. They really wanted to know what was further north. The reason they were so ignorant is that the local rulers of the countries north of the Himalayas were fanatically hostile and suspicious about foreigners, and they did almost anything to keep foreigners out of those countries. Various people tried to go there. These people are on an expedition. They're disguised as, in local dress. William Moorcroft was this man's name. And he entered Tibet about 1812 to try and see what was there, and he never came back. He was discovered and killed. Someone else had a go later. This is George Hayward, who explored the western Himalayas in the early 1800s also. Again in disguise, but again he was discovered and he never came back either. He was killed. So clearly this policy of trying to explore what was beyond the Himalayas as a European in disguise didn't work. Then what happened about 1860 was that the outfit which was responsible for making maps in India, which was called the Survey of India, had an idea. They thought, well, perhaps what we should do is train local people in how to make maps and send them north of the Himalayas, disguised as traders and pilgrims, and they can come back and tell us what's there. And what they did was equip these people with really quite interesting stuff. Pilgrims in those days used to carry a string of beads like this, and the beads were for counting your prayers as you said them, recited them, to know where you had got to. And the traditional Buddhist string of beads would have 108 beads on it. Well, the Survey of India's had 100. And this was so they could count their paces as they walked along, and they could see how far they'd traveled. The other thing they used was this sort of thing, which is a prayer wheel. And the idea is that inside this wheel there are some sacred text or prayers, and as you whirl the thing, your prayers get sent to heaven. Well, the Survey of India's prayer wheels had a little secret catch. It would open up, and inside would be a compass, so you could see which direction you were walking in. They had hollow tubes in the prayer wheels so that you could write your observations on little scrolls of paper and hide them inside these tubes. They had other instruments. They had an instrument to measure their latitude, how far north they were. They had something else to measure the elevation, how high they were above sea level. And this policy, these agents they sent to the north, were incredibly successful. This man here, in this book, is a man called Kishan Singh, who disappeared into Tibet and came back 4.5 years later. By the time he returned to India, he had long since been given up for lost, and he had made the most amazing journey. Let's see where he went. Kishan Singh entered Tibet. Here's Lhasa, the capital of Tibet, and he walked northwards. And he walked northwards all the way up to Mongolia, right in the north, and then back, going eastwards towards what is western China, all the way back to the capital Lhasa of Tibet, and then out into India. This huge journey was 4,500 kilometers. And when he came back to India, he came back in a different place from where he left off. The survey knew where he was. And after all this journey, all this making his measurements, he was only 16 kilometers out after this enormous trek. It was the most stunning feat of map making. It totally bowled everyone over at the time who were making maps. And the Survey of India produced this volume to record his journey. And it remains today. I find this absolutely amazing that anyone can walk that far and be so accurate. Now, I'm telling you all this because Kishan Singh and his fellow agents, they came back with stories of this huge area to the north of the Himalayas, which is called Tibet. Tibet is the most enormous place. It's 1,000 kilometers north to south, 3,000 kilometers across, and 5 kilometers up in the air. It is huge. There is nothing like this on the Earth anywhere else. And as these agents came back, it became clear that the Himalayas along the front are really just the icing on the cake. Tibet is the big mystery. What is this huge plateau behind it? Certainly, the Himalayas go higher. They go up to about 8 kilometers, the highest peaks. But for every high peak in the Himalaya, there are these deep valleys all the way around it. And the average height in the Himalayas is actually rather less than Tibet. And as you go north from India, the height just increases gradually, the average height, until you reach Tibet at 5 kilometers. Now, Tibet remained inaccessible throughout the 19th century, the early 20th century. Odd explorers tried to go there, but it was very hard. The conditions were extremely difficult in climate, and the people were trying to keep you out. But even in the 1970s, when I was a student, the best accounts of what were in Tibet were from these early explorers. And I would be looking at their accounts, trying to work out where the various geological things they had observed were. And it wasn't until the later 1970s, when we had pictures from space, that we could really see what we're dealing with. Here is a photograph taken from space. You can see the scale from the curvature of the Earth on the horizon. And we're looking along the Himalayas. These snowy peaks here are the Himalayas. India is on the left. And on the right is this huge plateau of Tibet, this high, fairly flat area. And this is the curiosity about Tibet, that it is really rather gentle, undulating country. Here's a picture of Tibet, rather flat and boring. When one of my colleagues first came back from Tibet, he said it looks a bit like the Cotswolds, but it's covered in yaks instead of sheep. Yak is a kind of hairy cow. Here is a yak. And in the background, we're looking south now, the Himalayas, which do stick up a little bit above Tibet. But as I'll say again, Tibet was the big mystery. What is this place? The most dramatic feature on Earth, really, and no one knew what it was. Well, before we continue this story, I need to remind you of the story so far, really, in these lectures. The Earth's surface is divided into a sort of mosaic of plates. Here they are. And these plates move around. And the point about this mosaic of plates, as we're looking at it here, is you can't really recognize where the continents are from the shapes of these plates. The continents are really just passengers. If I take this one off, for example, there's Africa hiding underneath it. Right? But the borders of the African plate are not the edges of the African continent. As I say, we were just regarding these things as passengers sitting on the plates. As we'll see in this lecture, they're actually more interesting than that. And let me remind you of how these plates actually move around. This is a map of the Pacific seafloor with the water taken away to remind you that the plates are created at mid-ocean ridges. Here's the ridge in the southeast Pacific here, where seafloor and the plate is created by seafloor spreading, and it moves away from the ridge and is eventually destroyed in the deep trenches around the edge of the Pacific, like around here near Japan in the northwest. And the plates move from the ridges to the trenches. And all you need to know about plate tectonics, the beauty, the simplicity of the whole thing, is that to find the borders of the plates, the edges of the plates, you just need to know where the earthquakes are. You just join the dots on a map of earthquakes, that's your plate. To find out how fast they're moving, all you need to know is how fast the ridges are spreading, and we know how to do that too. Now you can see the problem in Asia. If we come back to Asia and look at a map of the earthquakes in Asia, here are the earthquakes. Tibet is this big, high, white region in the middle. You can see there's no problem joining the dots in the oceans. Here's a mid-ocean ridge in the Indian Ocean. Here are trenches in Indonesia and in Japan up here. No problem at all, nice narrow bands of earthquakes. But what do we do in Central Asia, in Tibet, and this area here? How can you possibly join the dots? They're spread out all over the place, these earthquakes. And remember, the earthquakes happen when rocks break or slide about. So the earthquakes are telling us that things are going on. You can't possibly join the dots here. It's a crazy thing to think of doing, except that it's so easy to do in the oceans. And when plate tectonics was discovered in 1967, it was immediately obvious that the continents were doing something odd. Couldn't quite understand what was going on. You can't find where the plate boundaries are on the continents. And it took much, much longer to sort out what the continents were up to. And it's really only in the last 5 years or so that we have a kind of language for talking about how the continents work. One of the first clues along the way here is that the continents are very, very old. And I have here a rock from the continents. This rock I'm holding in my hand is about 3,000 million years old. That's incredibly old. The Earth itself is 4,500 million years old. And this rock is getting on then for that sort of age, for the age of the Earth. And then when I tell you that the oldest rocks in the ocean, the oldest rocks you see on the seafloor, are only 200 million or even less, we can see there's a huge difference. The difference between 3,000 million years old for the continents and 200 or less for the oceans is huge. The oceans are really young and the continents are incredibly old. And that's an important clue to what's going on, which we have to deal with. Now, let's return to our problem in Asia. One of the things we learnt how to do in an earlier lecture was how to rewind the continents to take them backwards to where they were in the past. And that's an obvious place to start, and we'll do that now. Here is what the continents looked like 150 million years ago. India tucked up against Africa and Antarctica. This started to break up. India breaks away from Gondwana land, that supercontinent, about 100 million years ago, and moves north towards Asia. And as it gets closer to Asia, it's slowing down a little now, and here it is in its present position. Now, as India was an island in the Indian Ocean here, the whole of that ocean between India and Asia was vanishing underneath Asia. And we need to remind ourselves of what actually happens. This is a model to show what happens in a trench, where, in this case, the seafloor is going to be sliding underneath the land. And this could be India as a passenger or an island in the Indian Ocean, with the Indian Ocean seafloor here sliding down underneath Asia. This would be Asia, southern Tibet. Let's remind ourselves what actually happens. As we move this, let's move it, we get shallow earthquakes here on the interface between those two plates as they go down. As this plate is being pushed down into the mantle, we get deep earthquakes within this plate here. These red lights are showing deep earthquakes in the plate going down as it breaks up. Now remember that these rocks which are entering the trench on the seafloor are wet rocks. They have water in them, and that water is what triggers melting down here. So somewhere down here we have melting, and that magma rises to the surface. A lot of it will freeze here to make granite, but some will come to the surface as volcanoes along the top here, along the southern edge of Asia. And all this is fine. We actually do see in southern Tibet big areas of granite that would have been formed as the Indian Ocean was sliding underneath Asia. All that is fine. We see that, and on top of that granite will have been volcanoes of this sort. Okay. But now let's see what happens when India actually gets closer to the trench. So let's just move India right up into the trench then, Bipin, please. Right there. And now what's going to happen now? What we see today is no volcanoes at all in southern Tibet. There are no active volcanoes, nor are there any deep earthquakes anymore. They've all switched off. India is not going down the hatch. It's not being pushed back into the earth anymore. Something else is happening instead. One thing we know is going on is that India is still moving. This is not like a car crash where everything just stops. We know from the spreading in the Indian Ocean ridge that India is still moving north towards Asia at about 50 millimeters per year. Now, it was moving much faster. It was moving at about 150 millimeters per year before the collision, and it slowed down to 50 millimeters per year now. But since the collision, about 40 or 50 million years ago, India has shoved about 2,000 kilometers into Asia. That's a huge distance. That's from here to Rome. India has ploughed into Asia. And obviously that is something to do with why the Himalayas and Tibet are there. But how? Well, the next thing you need to know, before we carry on, is just what are the continents made of? The continents are made of different stuff, different rocks from the seafloor and the rest of the plate. A typical continental rock is this one here, this light lump of granite, a smaller piece here. And that is very different from the typical mantle rock, which is this green rock, peridotite, which we've seen before. The big difference between granite, the white rock, and peridotite, the green rock, is that the granite is much less dense. It's rather light. In fact, it's so light that we can see that our passenger, India, suddenly no longer looks like a passenger, it looks rather like a life jacket. So here's this plate coming towards Asia, and it's got this buoyancy aid on it. It's India, huge, great thing, which will not go down the hatch into the earth at all. It will stop the plate going down because it's so light. That's very, very important. The other thing which is important is that this granite is always a lot weaker than this mantle rock, this green peridotite. And the reason for that is that the granite will melt at about 800 degrees, whereas this green peridotite won't melt till about 1300 degrees. And what determines how strong a rock is how close it is to its melting temperature. Because granite's always closer to its temperature, melting temperature, the granite is much weaker. So the two messages which matter here are that the continents are very light, and they're also very weak. And because they're weak, they will actually flow rather more easily by creep than will the rocks of the mantle. What we want to do now is to return to our Asia problem. Thank you, Milton. If India has not gone down the hatch, what has happened instead? Well, let's go back to our map. And one of the rather surprising things about the Himalayas and Tibet is that we can actually identify a boundary, which is the boundary between rocks that used to belong to India and rocks that used to belong to Asia. It's rather amazing that we can do that, but you can. And it's more or less follows this river. It's actually a smashed up zone of 2 or 3 kilometers wide, but basically rocks to the right of the river in this picture are rocks which belong to India, and rocks to the left are rocks which belonged to Asia. But that actually doesn't help us very much. When we look at the map of the earthquakes in this region, that line separating India rocks from Asia rocks is somewhere in the middle of all these earthquakes here. And we can see that the earthquakes are spread out much further than that. So whatever's going on is not restricted to that line, that geological boundary. It's spread out rather more. Now, why do I think these earthquakes way out in Central Asia have anything at all to do with India? They're an awfully long way away. These earthquakes here are about 3,000 kilometers from India. Why do I think they've got anything to do with it? And to try and convince you that they have, we need a demonstration here. And I'm going to need 3 volunteers, please. Right, let's have you, please. And let's have someone, have you, please, second row up, and let's have you. Now, your name is? Gerald. Gerald. I want you to be at the end here, and you are? Lucy. Lucy in the middle, and your name? Naomi. Naomi, at the end here, please. I'll explain to you what I want you to do. I have here 3 blocks, which are sort of India-shaped blocks, as you can see. And let's bury them in the sand. You hold that middle one, please. You have to keep pressing it down as you do it. And we'll do it quite slowly. It's not a race. I just want you to push it as far as my finger. You ready? Okay, go. That's it. That's it, doing fine. When you get your Indias as far as my finger, just stop. Thank you. Stop and keep going a little bit. Thank you. That's excellent. Right, you can let go now. What have we found? In this little, rather tiny weeny India here, the sand has buckled up only a little bit in front of the India block. It comes about this far. Here's a rather bigger India, and the sand has crumpled up all the way out to here. Here's the biggest India, and the sand has crumpled all the way out to here. Now, the distance that the sand crumples up in front of your block is about the same as the width of your block. So that distance there is about the same as that distance there on all these models. And the bigger the model, therefore, the more it spreads out. Thank you very much. This very simple demonstration is telling us that perhaps it's quite reasonable that we get earthquakes 3,000 kilometers beyond India, because India itself is about 3,000 kilometers wide. Very simple demonstration. But suddenly I'm talking about pushing things through sand. This doesn't sound like plate tectonics. It's a completely different kind of language. And you're right, it is a completely different kind of language. This is the way we're going to go. But it does sound as though we're on the right track here, and that's important. Now, to carry on this story, that we have to return to our friends in the survey of India. And about 1840, the Survey of India was run by this man, George Everest, after whom Mount Everest is named. And it was his business to make maps of India. Now, I need to tell you how you make maps of somewhere like India. What you do is you have to make a certain number of points. You have points around the country whose position you know very, very accurately. And then once you have those few points, you can make the rest of your map by just seeing where you are relative to those points. And the way you make those points is by a process called triangulation. Now, I want to demonstrate how that works, and I'm going to need 3 volunteers. Have you please, and the girl behind you, and yes, 3. You 3 here will do fine for the moment. Right, now, this is a complicated one. Your name is?
Sammy.
Sammy. I want you to stand about here, please, if you could. Just, you don't have to do anything at the moment, just stand there. Now, you two are? Alice and Catherine, right. Alice and Catherine, you stand here, please. One of you there, and a little bit to the side here. Alice, can you just stand here, just there? Right, now I'll explain to you what you're going to do. I'm going to give you each an arrow, 2 arrows. 1 arrow, that's all you need for the moment, and you need an arrow too. Now, I'm going to explain to you how Everest started to find these points, these precise points from which he made his maps. You start with 2 points whose position I know very accurately. Here's Alice and Catherine. I know where they are, and I've measured exactly how far apart they are. So I want you to hold hands, to just like that, straight, just to show that, yeah, I know how far apart you are, I know exactly where you are. Our problem is to find out where Sammy is. Now, what you do with your other arm is you hold your arrow out, please, at right angles to yourself, just sticking out there. That's fine. Now, what you then do is you move your arm in so it's pointing directly at Sammy. Can you just move your arm so the arrow is pointing directly at him? Right? Okay, good. Now then what I do is I measure very precisely the angle between your 2 arms, the angle between Alice's arms here, the angle between Catherine's arms here. And then because I know exactly the distance between these 2, and also those angles, that fixes precisely where Sammy is. Now what we do is this. You can just stand back here, Alice, for a moment. I'm going to give you another arrow. And I need another volunteer. Another volunteer? Yes, you'll do fine, actually. Thank you. Your name is? Edward. You're going to stand just here, okay? And I'm going to give you an arrow in a minute. Now, let me just get this right. You need to pick up your arrows, please, Sammy, okay? And you've got 2 arrows. I now know the position exactly of Catherine and Sammy, so I want them to point your left hand at Catherine and your right hand at Sammy, okay? That's it, stick your arm, that's it, absolutely fine. Point straight at each other. I know exactly now the length of that line. I know exactly where these 2 are. Our job now is to find out where Edward is. So what you do is you point your other arrows at Edward, and again what I do is I measure exactly the angle between your 2 arms and your 2 arms, and that fixes exactly where Edward is. And we can carry on this process. Now Edward can have a couple of arrows. Thank you. I'll just borrow one of your arrows here. And you might need to find, for example, where I am. So now what happens is you point at each other with your left arm, your right arm. That's it. And now you point the other arm at me. And again, we measure those 2 angles. And so what you do is you build up a series of triangles in a sort of corridor across the countryside. And that shows you where all these points are. Thank you. The way you measure those angles is by this device here, which is called a theodolite. And this is a 19th century theodolite, the sort that Everest would have used. And what it does is rotate. It's a telescope, and it rotates. And it's got a scale on the side, so you can measure very, very accurately that angle between the 2 arms of those people. And that's what you do. What Everest did was this. He measured a corridor of points from central India here up towards the Himalayas. And this was about 600 kilometers long, this great corridor. And of course, by the time he got to the end, he knew exactly where the end point was. He knew exactly where the start point was. He knew the length of the line between the 2. And like all good scientists, he thought, well, how do I check that? Is there some other way I can check that measurement? And there is another way you can check it, and we're going to show you how that works here. It's called star sighting. What we have is 2 points on the Earth, one here and one here. And you look at a star in the sky. Here's our star. And Bryson is going to hand me some light beams from this star. Here's one light beam, which is going to be observed here. And here's another light beam, which is going to be observed here. Okay. these sticks are the vertical, wherever these people happen to be. You know where the vertical is. You just take a weight on a string and you hang it, and that hangs vertical. That tells you where the vertical are. That's what these sticks are supposed to be. And what you then do is you measure the angle between the vertical and the light beam. In both these places, you actually use this same device, a theodolite, which can measure vertical angles as well. And you'll see that these two angles are different because these places are quite far apart. As I bring this point nearer to the other one, the angles become more and more the same. So the difference in those two angles tells us how far apart those 2 points are. That's the basis of this method. But what Everest found, was actually a big surprise, that these two methods actually gave different answers. That there was a difference between measuring the length of the line by star sighting and measuring it by triangulation. And the difference was 162 meters, it turns out. Now you might think, well, 162 meters over 600 kilometers, who cares? He was worried. The Victorians were superbly good at triangulation. I mean, they were really amazing. Until we had this satellite-based technology, which we talked about earlier, we couldn't do better than they could now. They were really excellent at it, and Everest knew that his results should have been good to 10 meters, or perhaps even better than that. And here he was, 162 meters wrong. And he didn't really know what was going on. And so he published his results saying, something's wrong, but I'm not quite sure what. And this got taken up by the most unlikely person. So the next person in this story is this man whose name was John Pratt. John Pratt was an archdeacon in Calcutta. An archdeacon is the sort of bishop's number 2. He's a clergyman. And he was one day reading this account of Everest in the Survey of India records. Goodness knows why he would be reading such a thing. But he was, and he was reading about Everest's puzzle, and he said, I think I know what's going on. He said, this is the problem. The problem is measuring the vertical with star sighting. Here's your weight hanging at the end of a string. But next to this weight on the string, we have the Himalayas. Here's the Himalayas. I'm going to put a yak on the Himalayas just to remind us that Tibet is actually the real mystery way out here. He said, here's the Himalayas with this great mass of extra rock. And of course, they're going to have a gravitational attraction, which is going to pull our plumb bob a little bit towards the Himalayas. Here it goes. It's moving towards the Himalayas. Right. So it's not hanging vertically anymore because of the attraction of this extra mass next door. Now, this amazing man, Pratt, the clergyman, then went on. He said, and I know how big the Himalayas are, more or less. I can work out how much that gravitational attraction should be. I can work out how much the plumb bob should have moved. And he came up with the most amazing result. He said, it shouldn't, your error was 162 meters. It should have been 500. It should have swung much more, right over here. It's not actually swinging enough. The Himalayas are not having the effect they should have. Pratt then went on to say, he said, well, if the Himalayas are not having the effect they should have, perhaps the Himalayas are made of different stuff. Maybe they're just made of very light rocks, and they're not having the attraction they should have. But at that time, someone else comes into the story, a man called George Airy. George Airy was the astronomer royal. He was back in London, and he was reading about Pratt's extraordinary calculations. And George Airy came up with another suggestion. In fact, he had two ideas, really, and we're going to show those ideas in this next demonstration. Airy had two ideas. He thought that the Himalayas were likely to be made of the same rocks as India, say. Then he thought that the crust of the Earth, the surface we're walking on, is actually floating on a magma lake. We've heard this one before. He thought that we were floating on an underground lake of very dense molten rock. We'll come back to that. Let's follow his argument for the moment. So he said, well, here's India floating on this lake of dense liquid. And he said, well, perhaps the reason the Himalayas stick up is because actually the crust is thick. So if I put in, this is supposed to be Tibet here. If I put this in the tank, this sticks up because it's thick. And he thought, well, maybe that's why the Himalayas in Tibet are so high, because they have a root. Now, what's going on here? He went on to say, well, the reason that the Himalayas are not attracting that weight at the end of the string so much is this. Underneath India, we have this very dense, heavy liquid. Underneath Tibet, that dense, heavy liquid is missing. We've got this light stuff instead. We've got this crust. And so the reason the plumb bob is not swinging so much is because there's stuff missing underneath. It's dense stuff missing underneath Tibet which matters, not so much the extra stuff at the surface. This was a big contribution. He made us think that Yes, it's what happens underneath which matters, not just at the surface. And it turns out that Airy is right, that the Himalayas and the Tibet do have a deep root. We know that by sound. We can send sound waves down there and bounce it off the bottom. This is the way we look inside the Earth. Of course, Airy was wrong about the magma lake, the dense liquid underneath. What's underneath is the mantle, and it can flow, of course, by creep because the rocks are hot. We've met that in every lecture so far. So this is why the Himalayas stick up, and it's actually why nearly all mountains on continents stick up, because they have deep roots like this. But the next question is, well, where do these roots come from? To find out where the roots came from, we have to return to the mountains to see what evidence is there. When we look at the Himalayas, you see this kind of thing. These are layers of rock which were originally horizontal, and now they are buckled into a great fold, as though someone has just squashed it sideways. They've just crumpled up. A view from the air of another part of the Himalayas looks like this. There's all this squiggly stuff in the mountains, which are folds. It's all just bent and contorted because it's been squashed up. We see lots of examples of great sheets of rock pushed on top of each other, again, as the mountains have shortened and been squashed up. And you see it on all scales, even down to this kind of scale of rocks that have been folded and squished up, like a concertina. And that is how the roots get thick. That's how the crust gets thick, by getting squashed up. And I can show you this in this demonstration here. Here we have, in our demonstration, the crust, represented by some white beads here, floating on the mantle, the denser stuff underneath. Now, what I have here is a shutter, which we're going to pretend is India now, which is going to bash into Asia. And let's see what happens as I move it towards Asia over here. As I move it, it's getting thicker and thicker. And it's piling up. And look at this huge root underneath. This is how we make these thick roots, by shortening. And when we look at the Himalayas and Tibet, the root is quite extraordinary. The Himalayas, as I say, Tibet sticks up about 5 kilometers into the air, but the root goes down to 70 kilometers. It really looks like this. I still find this astonishing. You look at these big high mountains and think, wow, they go up high, but they go down 14 times further than they go up. It is a huge effect. This root is enormous. And the other thing which this little tank shows me, which is important, is that I have to keep pushing to hold this thing up. And what's doing the pushing to hold it up is India on this side and Asia on this side. And the higher the mountains and the thicker the root, the harder you have to push to hold it up. And if I had to take the shutter away, it'll all start to flow away, fall down. So something has to be holding up, and that's a very important clue for later. This is how mountains form, by making the thick root, which makes them stick up in the air. And that is why, when you go to the Himalayas and Tibet, you find things like this. This is a fossil I'm holding, and it's a marine fossil. This creature used to live in the sea. And it has no business being 4 kilometers up in the air in Tibet, which is where this thing was found. It's got up there by the crust being crunched up and shortened and thickened, and that's what pushes it up into the air. And there are other consequences of the crust having these roots too. Let's look at this again. Here's our same model. And I have thick crust over here in Tibet, next to thin crust in India. And the tops of the mountains are being continually eroded. They're being eroded by the wind, the rain, by ice, the tops falling off in landslides, faults can take the top, all sorts of things can go on. And we can remove the top. And let's see what happens when we remove the top. Let's look, for example, at this yellow layer, which is really quite deep into the crust of Tibet. As the top is removed by erosion or landslides or faulting or whatever, the bottom bounces up. The root bounces up to the surface. And by taking the top off, I actually get that yellow layer right to the surface. And it still sticks up. It's still a mountain, but I'm seeing at the surface rocks which actually belong way down into the earth, really very high pressure rocks, which we would otherwise not see were it not for this effect. And when you look into the core, the heart of the mountains, like the Himalayas, what you see are these rocks which formed under very high pressure. And I've produced some here just to show you that you get things like garnets, these big red crystals here. Here is one crystal of garnet, a huge, great crystal of garnet, which is really quite a high pressure mineral. other minerals you get are like this blue mineral, kyanite, which again belongs 10 kilometers or more into the interior of the Earth. This is a high-pressure mineral. It has no business being at the surface of the Earth. It's there because the roots have bounced up underneath it and exposed it at the surface. One of the most dramatic high-pressure rocks is this great big green boulder at the back there, which is jade. Jade is a very prized rock. You find it in China, in Siberia, in New Zealand, anywhere where you can look into the core of mountains deep down. The tops of the mountains which get worn away, eroded, what happens to all that stuff? That stuff gets washed into rivers, ends up, in the end, dumped on the seafloor in the ocean. But then when that ocean comes to a trench, which is what all oceans do in the end, they come to a trench, that light sediment sitting on the top just gets scraped off and it gets slapped back onto the continent. And what we've done is actually solve one of our earlier mysteries. The reason why the continents are so old is you can't get rid of them. They just sit around, they bash into each other, they will not get pushed into the interior of the Earth. If you erode them, the sediment just gets scraped off again and slapped back onto the continent. You really can't get rid of the continents, they're here to stay. That is one mystery which we've cleared up. Another mystery which we need to clear up is, why is it that the Himalayas don't just seem to go on getting higher and higher and higher and higher forever? Why does it spread out to make this great plateau called Tibet? Now, if you remember that bead tank, I said I had to be holding it up. I had to be pushing to hold up that big, thick root. And what's doing the pushing, what's holding it up, is Asia and India. And Asia and India only have a certain amount of strength. They can only hold it up so high. Right? It can't go any higher than they can hold it up. And once they've got it up as high as they can hold it, all that can happen, if India keeps pushing more material into Tibet, all Tibet can do is just grow out wider and wider and wider without getting any higher, to make a plateau. And I can show you the effect in this sand model here. That I have, here's this big India block again, and I'm going to push it through the sand, and let's just see what happens in front of it. As I push it here, the sand is crumpling up in front of it, and it just gets to a single height, and then all it does is move out. It stays at the same height and just gets wider and wider and wider and wider. And out in front here we have a high plateau, which just grows outwards with time. And that is why Tibet is there. That is the reason for that high plateau. So in the end, the key to understanding the mountains, why the mountains are there, why the plateaus form, is that the rocks are weak and they're also light. They will not get pushed down into the interior of the earth. All they can do is grow outwards to make plateaus, but the heights of those plateaus are actually controlled by the strength of the surrounding rocks. And that is why all mountains do this. If you look at any of the big mountain ranges in the earth, they have spread out with time. That's how they grow. And 5 kilometers, the height of Tibet, is about as high as we can get these plateaus on the earth because they're held up by the strength of the surrounding rocks. And the surrounding rocks are only strong enough to make something 5 kilometers high, not more than that. The only other place on earth which is remotely like Tibet is the Altiplano in the middle of the Andes. That's at 5 kilometers also, but it's very, very much smaller. Continents don't just collide, they don't just crash into each other. They can also do other things like break up. And we've seen that before. We've talked about Gondwanaland breaking up. And if continents are so strange when they collide, what happens when they break up? Let's have a look. Let's remind ourselves. This is a picture of the continents 150 million years ago, the supercontinent Gondwanaland, which, as we've seen now several times, broke up. And it broke up to make the southern continents there. And there are still parts of this which are breaking up today, especially Africa. Let's have a look at the earthquakes in Africa. Here are earthquakes in Africa. Notice once again the very narrow band of earthquakes in the Atlantic Ocean here and in the Indian Ocean over there. And once again on the continents, the earthquakes are spread out. We're used to this by now. This is the great feature of the continents, is that the earthquakes and the faulting does spread out. And it's spreading out as Africa is breaking up, and the eastern part of Africa is pulling away from the western part. And having seen that when you crunch up and shorten the continental crust, it gets thicker, you're not going to be surprised when I say if you stretch it, of course, it gets thinner. It necks. Of course, the lower part of the continental crust will flow by creep where the rocks are hot, but the top part, the part we're walking on, is rather strong. And that doesn't flow, it does something else, and let's have a look. I need a couple of volunteers. May I have you two? Your names are? Elise and Alexander. Alexander, will you come this side here? And I want you to hold on to this. There's a little handle here. Just hold it gently, right? And Elise, will you hold that one too? You've got it, just pulling it gently. So we have this under tension now. We're going to stretch it. Now I want you to pull quite hard as you can. Oh, you're making it lift off. Really hard pull. 1, 2, 3. That's it. Great, thank you. What you've made is a rift valley. Thank you very much. What we made is a rift valley bounded by faults. These grey areas here are fault escarpments which have dropped down the rift valley. In other words, of course, the surface of the Earth, which is cold, doesn't flow, it busts, it breaks on faults, which is why we get earthquakes. The most famous rift valley on Earth is, of course, the East African Rift Valley, and let's look at what it looks like. Here's a picture looking along the East African Rift Valley, along the escarpment or fault, and it's a big high cliff, about 1 kilometre high, with the Rift Valley on the left and the higher ground on the right. The next picture, we're going to look at the escarpment itself. Here we are looking at the fault, just to show you how high it is, about 1 kilometre high, with the Rift Valley in front. Now, of course, we don't just get one fault, we get lots and lots of faults, which is why the earthquakes spread out, and each of these cliffs here is a fault, and the East African Rift Valley is made of lots of these things. Now, although the East African Rift Valley is very famous, it's not actually moving very fast. It's stretching by just a few millimetres per year. By far the most rapidly moving area of the continent that's being stretched today is much nearer home. It's actually in Greece. And let's look at the earthquakes in Greece. Here's Greece over here. And I'm showing you now just 5 years' worth of earthquakes. There are an incredible number of earthquakes in Greece. And Greece is slowly disappearing under this cloud of earthquakes that I'm showing you here. Fortunately, most of them are not too big, and a lot of them are in the water, so they don't do as much damage as you might think, looking at this dreadful map, which now Greece has completely vanished under it. I can't show you where Greece is anymore. But we'll have the next map, which shows without the earthquakes. Between Greece and Turkey is this light blue area, which is called the Aegean Sea. Now, it's not true ocean. It's really just sunken continent. It's a continent which has stretched and necked a little bit, and it's just sunk below the sea surface. The water depth here is only 100 meters, a few hundred meters, not very much. True deep ocean seafloor is south of Greece, this dark blue color, where it's about 3 kilometers deep. That's the real thing. But this is just stretched continent. Now, as I said, it's the crust stretches and gets thinner, but the top part busts to make rift valleys. And those earthquakes in Greece are doing just that on faults. So let's look at what these faults look like in Greece. Here is a fault which moved in an earthquake in 1981. It sliced up this road about 1 meter offset here, and that's my rucksack sitting on there to give you some idea of scale. The next picture shows the same set of earthquakes. You can see the bit which moved in this last earthquake, which is stained red here from the soil in the valley, which stained the fault surface, and this fault surface continues upward. So that this has moved before. That's the simple message. And that cliff has formed through several earthquakes. And we're just looking at the last one. As we stand still further back from these things, here's a person in the corner for scale. This is one of these big polished fault faces, and you can see these striations. They're like sort of nail marks clawing down the rock as the front is sinking, it's dropping down, and leaving these scratches behind on it. As we stand still further back, these polished rock faces would be here in this cliff. We're looking at a whole mountain which is formed by just more and more earthquakes dropping down the foreground. In the foreground are houses which were destroyed by the last earthquake here, and this whole mountain, which is about 1 kilometer high, has formed in about 1,000 earthquakes at 1 meter at a time each. Standing still further back, that last picture was taken looking at this mountain here. In the foreground is a village which was destroyed in that earthquake, and here is the sea. And because the whole of this front region, in front of this fault cliff or escarpment here, is sinking, it's actually falling into the sea. And the next picture is a close-up of this beach, with the fault in the background, and there isn't any beach anymore. After the earthquake, the beach had gone. This used to be a rather pretty little bay for swimming with a beach. It's gone. And here's a restaurant which had to pile rocks up in front of it to keep the sea out. And just round the corner from this picture is me standing on a jetty, which was the harbour for this little bay, and I'm up to my knees in water, standing on the harbour jetty. It's sunk about 1 meter. And just round the corner from here is a church sitting in the sea as it sunk down. And this is why the sea is where it is. The sea is here because the coast is sinking in front of the fault, which is the big escarpment, that hillside in the background. And one of the things we've been doing, my colleagues and I, over the last few years, is trying to see how the whole of Greece is changing shape as a result of all these faults moving everywhere and all these earthquakes. The other thing we can do is measure the distance between points using this satellite technology, which we talked about in a previous lecture, and we can see exactly how Greece is changing shape. And to show you how it's changing shape, we need one more demonstration. So I need some volunteers. So I have you, please, and you behind in the black shirt, and let's have a couple more. Yes, you, and yes, would you like to come too? You can get out. Right, now your names. Eleanor. Simon. You stand this side, and would you, your name? Satma, come over here, please, and your Marcus stand over here. Now what we're going to do is show you how Greece changes shape. I want you to hold on to that very hard, both hands, and I want you to hold on to this end here. Now let's move you a little bit over here so we can see about here, and tilt it slightly that way so that people can see. Let me point out what this map is. This is a map of Greece. Here is Greece. This is Turkey. Crete is down here, and this blue area is the Aegean Sea. Athens would be about here on this map. And what I'm going to ask my assistants to do here is to get a really firm grip on this, right, really hard, and now really pull it as hard as you can. All right, great. We're stretching Greece. Stop there, thanks very much. And the whole of Greece has stretched. And this is what it's really doing. Greece has stretched about 200 kilometers in the last 5 million years. And it's stretched rather like this rubber sheet. The reason the outline of the map is so strange is because of what I'm going to show you next. Don't worry about that. But we've seen Greece stretch in a north-south direction by this rather large amount. Thanks. Let's release this before it goes twang. Thank you very much indeed. What we've done there is not fanciful. That really is what Greece has done. And I want to show you now the real maps, the maps my colleagues and I put together to see what really happened, just to show you how similar it was to that. Here's what Greece looks like today, and that's why the map had a funny outline. It's the same shape as this. Let's take it back now to 5 million years previously. Here's what Greece looked like 5 million years ago, and it's going to stretch in the north-south direction. Let's scroll it forwards now to see how it changed shape from 5 million years ago. Here it is coming forward to the present, and now let's keep going for 5 million years. Here's how it looks. This is how Greece is changing shape. Now, this all sounds very strange to you. Greece is not made of a rubber sheet. What am I doing talking about rubber sheets? Greece is this mass of faults. That's why there are all these earthquakes. And the thing is, you actually need both ways of looking at Greece to understand what's there. If you're interested in the general picture, yeah, Greece is changing shape, like these maps, like the rubber sheet. If you're interested in the detail of how it does it, then you need to know that there are all these faults which are moving, and that actually Greece is broken up into little blocks that are moving by those faults. This is not such a strange idea. Let me show you by another example. Over here, we have a picture which just looks like a lot of splodges of colour, just little blotches of colour. And this is looking at detail at this picture, and it's a picture of splodges of colour. Now let's move out. Let's move the camera out from this picture to see what it looks like when you stand back. As we stand back, it starts to have a different look. Yeah. Now, it looks like a picture of children on a beach with rocks. That's what we're looking at, a rock, and the sea in the background. And to understand this picture, actually, you need both ways of looking at it. You need to know that it's a picture of children on the beach playing with rocks and the sea in the background. But you need to know also that it's made up of those splodges of paint. And that's actually what you have, the language you have to speak when you want to find out about Greece, how Greece works. Yes, in general, it's like stretching a rubber sheet, but in detail, it's lots of little faults moving. Now, this is how then the Aegean Sea formed between Greece and Turkey, by this stretching, necking of the crust. And it's how lots of shallow seas around the continents have formed in the past. The most famous and most interesting to us is actually the North Sea here, between Britain and Norway. The North Sea is, again, a very shallow sea. It's only 100 meters or so deep. It's a bit of stretched continent. And it's stretched because England and Scotland moved away from Norway about 80 kilometers. But it stopped doing it 100 million years ago or so, whereas Greece is still doing it today. And the extraordinary thing is that now, of course, we know that that's how the North Sea formed, but we've only known that since 1978. the North Sea was being explored for oil long before that, right? And these basins collect oil because once you have a shallow area of sea like that, sediment washes in and so do dead plants and bacteria and algae and all these things which get cooked up to make oil. And of course, it's very important for the people looking for oil that they realize that these shallow basins or seas are formed by stretching. Why did it take them so long, till 1978, to find out what was going on? Because finding out what was going on didn't come from looking at the North Sea, it came from looking at earthquakes in Greece. And it was my colleague looking at earthquakes in Greece who discovered how the North Sea came to be there. And it's another example of the trick the Earth is always playing on us, that you look at one thing and you find out about something totally unexpected. Happens again and again. And now we can see, having talked about sand, pushing sand around for Tibet, about stretching rubber sheets for Greece, we can see that it's actually nonsense to ask the question, well, what plate is Tibet on? Or what plate is Greece on? Tibet and Greece are just smashed up zones of rock extending over huge distances. It doesn't mean anything to ask what plate are they on. It does mean something to ask what plate is London on, because London is in the middle of a huge area which is doing absolutely nothing at all. We don't have earthquakes here. We are firmly on the Asian plate, no question. It makes sense to ask what plate is Timbuktu on. Timbuktu is in the middle of another place that's doing absolutely nothing. That's the African plate. Okay? When we talk about places which are being crunched up on the continents or stretched on the continents, we need a different language. It's not the language of plates, it's the language of rubber sheets and sand. And we can say, really looking at the Earth, that the Earth is about 90% plate tectonics and 10% this other language, let's call it continental tectonics. And so you can see it's not very surprising that we had to discover about plate tectonics by looking in the oceans, because plate tectonics describes what happens in the oceans. It doesn't describe very well what's going on in places like Tibet and Greece. Now, the final mystery we want to talk about is, well, where have the continents come from in the first place? How were they formed? This actually is a much more difficult question than you might think. Although we can see continental rocks easily, these continents have been continually crunched up and stretched and melted and eroded and generally messed about. And the evidence of where they came from has largely been erased. That's really quite hard. And to be quite honest, we're not exactly sure, but I'm going to give you some idea of what we think is the position. In the end, the continents will have to have come from the mantle. Let's have a look at our cross-section of the Earth from the first lecture. The mantle is this green area here, and in the middle we have the core and the inner core. Now, the mantle is 85% of the Earth. The seafloor, we know, comes from melting the mantle. That's how you make the seafloor. And the continents, in the end, have to come from the mantle. There's not really much anywhere else they can have come from. The thing is, if we melt the mantle, what we get is this black rock, basalt, which we've looked at a lot in the past. What we have to find is some way of making this lighter-colored rock granite. And here's a piece of granite. Now, what is the difference between these two things? The difference is really in the amount of the element silicon that is in them. The basalt has about 45% silicon, the granite about 65% silicon. What can we do to the mantle to turn it from basalt into granite, to get it beyond basalt to make granite? Well, let me illustrate what might be going on by a different process. Here I have a bottle of wine, which has 12% alcohol in it. And here's a bottle of brandy, which has about 40% alcohol in it. How can I turn wine here, this stuff, into brandy? So let me pour a couple of glasses of this. This is the wine. And we've got to somehow get this into brandy. Now, the difference between these two is in the amount of alcohol. One way of increasing the relative amount of alcohol in the wine to make brandy is by removing the stuff which is not alcohol. And one way you could do that is by freezing it slowly. If we froze it slowly, what would happen is that the water would start to freeze first, because it freezes before the alcohol, and would settle out. We could remove the water. That would increase proportionately the amount of alcohol. Now, it takes a long time to do that properly, so I'm going to ask Bryson to do it not properly in one of his violent displays. Let's give Bryson a glass of this wine and see what he can do with it here. We're going to freeze this quickly, shoving it in liquid nitrogen. Now, okay, what is happening here is he's cooling this down to form ice, we hope, and leave some of the alcohol behind. I should stress you must not do this at home. not only is it illegal, but it will taste disgusting. And this is not how you make brandy, let me tell you, either, from wine. It's forming ice, which is actually crystallizing around the edge of Bryson's container. How are we getting on? And Bryson's going to pour it now into this glass. And there's a fair amount of ice around the edge of that container. And let's see if that glass now has a level which has gone down relative to the other one. A bit. But there's plenty of ice around the edge of that container, and Bryson can't pour it out. That is ice which is frozen. And the amount of alcohol will have actually gone up in this glass relative to the previous glass because we've removed the stuff which is not alcohol. What's happening in the earth? In the earth, we need to increase the amount of silicon here relative to this basalt. We can do that by removing the stuff which is not silicon in exactly the same way, by this process, which is called freeze distilling. How do you do it in the earth? We do it in the earth by water again. Think back to what was happening at the trenches. Those are wet rocks that are melting. That's why they're melting, because of the water. And water has a rather odd effect. If we get wet basalt and then start to freeze it, we actually make different minerals than we would make if we were freezing dry basalt. And the minerals we make first turn out to be very poor in silica. A lot of the other stuff, but not much silica. They form first, they drop to the bottom, so what's left behind is richer in silica than it would otherwise be. In other words, the secret to making the continents is water. And without water, we probably wouldn't have continents on this earth. This water is rather important stuff. We certainly couldn't live here without water. And now I'm saying to you that water is probably responsible for the very rocks that we walk around on. This water is important stuff. In the next lecture, we're going to look at other things water can do, and perhaps wonder about what our planet would look like if we didn't have any water. Thank you.